Okay, first I want to point out that this work is performed by the joint AOML CMUS Rasmus Ocean Modeling and OSSE Center, and key colleagues are listed here. Before I go into the talk, I'm just going to, for those who are not familiar with our Ocean OSSE system, just a one-slide summary of what it consists of. First of all, we have a nature run, which is a multi-year, unconstrained, run by an advanced ocean model that has been validated to represent the truth. And we use a high resolution, unconstrained simulation by HICOM for the nature run. And we have an ocean nowcast forecast system, which uses a different version of the HICOM model with substantially different configurations, what we call a fraternal twin OSSE system. Our ocean data assimilation procedure is a research procedure developed at OMOC, and it's designed specifically to work with the HICOM Lagrangian vertical coordinate system, which other DA systems don't explicitly do. In the OSSE system, of course, you have to simulate observations from the nature run, and at realistic areas, we have a toolbox that does that. And the important point about our system, it has been rigorously validated following best practices developed for atmospheric OSSE systems, which demonstrates that our impact assessments are credible. And this is, of course, the result of working with Dr. Atlas, who was a primary developer of atmospheric OSSE systems. Now, our OSSE plans, OSE and OSSE plans for TC prediction related work during 2018. We're going to use our system to evaluate the impacts of supplemental ocean observing strategies during recent hurricane seasons, particularly the last 2017 active Atlantic season. The present status of our system, we're bringing it up to date through 2017 now. Our nature run has now been extended and being evaluated at Rasmus. Philly Kroflu and Hisuk Kang and Jonas Androidakis are working on that. Since the last round of work we did with the OSSE system, we made some configuration changes to the forecast model. We're now using a different vertical mixing model compared to the nature run, familiar model versus KPP. The reason being is we saw the limitations of how the OSSE system worked during the last round of work, and we're trying to do a few things to make it work better for this new round of work. And because of these changes, we will do an additional OSSE system evaluation this winter and early spring, where we directly compare OSE and OSSE comparison experiments to determine if these configuration changes, hopefully they do make our system work a little bit better. This work is underway now, and I expect that we will be ready to begin to run our actual storm experiments by Q3 of this fiscal year, in other words, by April or early spring. So we have another month or two of evaluation, validation work to do. Because this work is in its early stages, for today's presentation, I'm going to present some very preliminary results in two parts. First, I'll describe efforts to improve the correction of ocean mesoscale structure by the assimilation of supplemental ocean profiler observations. In the second part, I'm going to summarize our existing scientific understanding, hopefully to guide the our expectations on how these supplemental ocean observing strategies will actually affect tropical cyclone forecasting. We'll be actually taking ocean fields produced by our OSE and OSSE system and using that to initialize a couple of hurricane prediction models. Motivation. Accurate short-term ocean prediction requires accurate initialization of ocean mesoscale structure. And in addition to improving TC prediction, is valuable for other forecast applications such as transport and dispersion of oil and marine debris, etc. So this work will impact a lot of potential ocean applications besides tropical cyclone forecasting. Supplemental ocean profiler observations have been previously conducted with the express purpose of improving ocean model initialization. Two examples on the lower left is P3 ocean profiler surveys conducted after the Deepwater Horizon oil spill. These type of surveys have also been conducted ahead of hurricanes to try to improve initialization ahead of storms. Lower right is our in-house Dr. Goni's project on underwater gliders, and hopefully we'll be testing how these types of deployments will improve tropical cyclone prediction. Other examples exist, such as Alamo float deployments ahead of storms, and adding thermistor chains to surface drifters and deploying those ahead of storms too. So there are a lot of types of pre-storm surveys, ocean profiler surveys that we will be evaluating. So the question is, how effective are these supplemental surveys? We need a quantitative assessment of how effective they are. We obviously need to detect the impact with respect to reducing ocean model initialization errors and subsequent forecast areas. We'll be performing observing system experiments to evaluate the actual observations that have been taken. But also survey design studies must be performed to determine the best ways to deploy these types of instruments to increase the positive impact. And for that, we will use the OSSEs, where we can deploy these instruments any way and at any times that we desire. We're using our system now to address these issues. OSSE systems provide a high-resolution three-dimensional representation of the truth by the nature run, and that allows us to rigorously evaluate how accurately our DA system, our data assimilation, is correcting ocean mesoscale structure. Now, the two parts of the talk, the first will be, of course, I'll talk about improving the correction of ocean mesoscale structure. I'll present idealized OSSEs that assimilate supplemental ocean profiler observations. I will first show that how this can be used to improve data assimilation system performance, especially with respect to improving the representation of ocean mesoscale features. I'll also present very preliminary results that evaluate deployment strategies with respect to trying to optimize profiler separation distances and understanding what aerial coverage we need to make a significant impact. In the second part of the talk, I'm going to summarize existing scientific understanding to try to determine how assimilating these supplemental ocean observations will likely affect tropical cyclone intensity prediction. I will discuss plans to directly assess observing system impacts on TC forecasts. And we're going to be, Leonoff is now working to learn how to run the HICOM HWRF coupled prediction system. And we'll be initializing that coupled system with output from our OSE and OSSE system to really begin to look at how these reducing initialization errors actually impacts the intensity forecast. But the existing scientific understanding I'll summarize was largely contained in a paper shown here, published in 2015. This will give us some clues as what to expect on how improving ocean model initialization should affect intensity forecasts. Okay, improving the profiler correction of ocean mesoscale structure. Our system, DA system, solves for each analysis increment is obtained by solving the equation shown. The background area covariance matrix, which is tapered by a localization radius function to eliminate observations too far from the model grid point being updated, spreads the innovation through model space to determine the analysis increment. And in our system, this covariance matrix is calculated from an ensemble obtained from an unconstrained simulation by our forecast model. The accuracy of analysis increments obviously are expected to decrease with distance from an individual profiler observation. As a result, the horizontal structure of the analysis increment, the correction made to the model field, may differ substantially from the actual structure of the true error field. The high resolution representation of the truth provided by the OSSE system allows us to actually examine that rigorously. The upshot of these issues, as I'll show, is that a single profiler will not accurately correct ocean mesoscale structure in its vicinity. And it's shown by an earlier run here, where temperature salinity profiles down to 1,000 meters were assimilated on 2 consecutive days. The upper left panel shows the total correction after 2 days of the assimilation. a correction to the model field. And on the upper right is the negative of the actual error field present at this time, which is obtained by the difference between the nature run and the forecast model. We know the structure of the actual error that we're trying to correct, and then we see the correction in the upper right. And what you see right away is that within the localization radius chosen for this, this calculation, the structure of the correction does not closely match the structure of the actual error that existed at the beginning of this run, which is loaded with mesoscale structure. The correction is actually quite accurate, very close to the observation, but farther away. The spreading of the innovations does not match the structure of the error field. So this leads to problems when you're trying to correct mesoscale structure in the ocean by adding ocean profiler simulations. The choice of localization radius involves a trade-off, accuracy versus error correcting. You want to correct as large an area as possible, but if you increase the radius that you're correcting, then an observation will correct the model. You're going to eventually introduce more errors and degrade the assimilation. So the OSSE system can be used to really understand more about this trade-off in a quantitative way. And to do that, I performed an idealized OSSE study by simulating synthetic CTD profilers. It was conducted within a 14 degree by 14 degree box in the open North Atlantic Ocean, where fixed synthetic profilers sampling temperature and salinity down to 1,000 meters are evenly spaced in degrees, latitude, and longitude within this box. And the first application of this that I will show will be to use this to determine what can we optimize the choice of localization radius to correct as large an area as possible around the observation without introducing too much additional error. And I'll show these results, and it illustrates the power of OSSE systems, how they can be used to improve data assimilation system performance. After that, I'll present some initial results that quantitatively assess the impact of horizontal profiler separation scales on reducing errors in mesoscale structure. So first, the idealized study. Basically, this analysis box shown on the right was seeded with profilers separated by fixed distances in latitude and longitude. And I have a list of the experiments performed here. There are 4 separation distances, 3.5, 2 degrees, 1 degree, and 0.5 degrees. They all have experiments run with a 200-kilometer localization radius. But for 2 of these, I ran 4 different, a total of 4 different localization radii as shown to get an idea of how that's impacting the correction of mesoscale error. Basically, these simulations were performed 1 May through 31 October, 7-month period. The analysis will be performed over the final 6 months of that period, allowing 1 month for equilibration to the assimilation. And to look at how they were affecting the correction of mesoscale structure, I used wave number autospectrum analysis, where it's calculated over the 6-month analysis time interval. Averaging is performed over zonal time, averaging for meridional autospectra, and meridional time averaging for the zonal autospectra to increase the degrees of freedom of the estimate. The black curve is the error spectrum. The error is defined as within that 14-degree box, the difference between the experiment and the nature run representing the truth. And obviously, the error spectrum is quite large for the unconstrained model. And for the 1-degree separation experiment with a localization radius of 200 kilometers, you obtain the following change in the error. As you can see basically with 1-degree separation, you can define a Nyquist wave number roughly equal to twice the profiler separation, which is 2 degrees or approximately 220 kilometers. As you can see, the error is reduced at wavelengths larger than that Nyquist value, but actually some noise is introduced and error is increased at the smaller wavelengths. So basically you are improving mesoscale representation of mesoscale features at scales larger than Nyquist, but you can't really use an array of profilers to improve errors at smaller scales. Now to look at the situation, try to understand the impact of localization radius. Here, the black curve again is the unconstrained forecast model, and this is for the 2-degree separation case. We have spectra of the on the left, the dynamic height relative about to 1,000 meters, and on the right, the temperature averaged over 0 to 100 meters. What you see is that the red curve is for the largest localization radius, and the error reduction is almost nil. But as you go to smaller localization radius, you do get greater error reduction. And it looks compressed here, but there's actually a fairly large reduction in variance. For example, for dynamic height, the reduction over, say, the upper half of that wave number range is between 150 and 250% by reducing the localization radius from 425 to 125 kilometers. Somewhat smaller for the upper ocean temperature average, 50 to 70%, but still fairly substantial. So you see a very strong impact on choice of localization radius. One thing you see is that the two smallest radii, 200 and 125 kilometers, the results are very close. So when you get down to around 200 kilometer localization radius, you're not gaining much by decreasing it because you're correcting a smaller and smaller area. For the 2-degree case, this is the same type of figure. Generally, you have a smaller reduction by reducing the localization radius, 30 to 60% for dynamic height, 20 to 40% for upper ocean average temperature. And again, very little difference between 200 and 125 kilometers. Therefore, for our work, we've chosen the localization radius to be 200 kilometers, the trade-off between large enough area and accurate correction. Okay, given that we have that localization radius corrected, here are results from different separation distances. And as you can see, the red curve at 3.5 degrees does not significantly correct error at all in terms of the improving the mesoscale structure. The observation is too far apart to accurately correct the structure. At 2-degree separation, you begin to see improvement at wavelengths again larger than the Nyquist, which at 2 degrees is about 440 kilometers. And then with 1-degree separation and 0.5-degree separation, you get very large error reductions. It's more than an order of magnitude at the 0.5 degrees. And but what this is telling us is that to use supplemental ocean profile observations to correct mesoscale structure, high horizontal resolution is very important. You get very, very, very good correction if you're sampling at order of 1 degree or smaller, but when you go up to 2 degrees or more, you're not getting that much error correction in terms of mesoscale structure. This is the same, the previous was for dynamic height, this is for upper ocean temperature, fairly similar results. And to get an idea, just in terms of looking at the maps of how the model is being corrected, on the upper right, we have this is the analysis increment for dynamic height on after 1 day of assimilation. Just one, we assimilated just once. And that's for the 0.5 degree case, upper left. Upper right is the same for the 2 degree case. And what you see is the fact that each observation cannot correct a sufficiently large area, and you get a polka dot pattern, if you will, in terms of how it's corrected. And that leads to inaccuracies down the road and error. That reduces the ability for the coarse resolution sampling to reduce mesoscale errors. For 0.5 degrees, the lower left panel shows a snapshot on 6 September 2014. So just the difference between the experiment and the nature run. In other words, it's the actual error. And you can see the large error reduction with the 0.5 degree sampling. Not so much for the 2 degree sampling. So resolution of the observations makes a big difference. This is the same for upper ocean average temperature. You see like what looks like a quasi-continuous analysis increment or correction pattern on day 1 with 0.5 degrees, but again, the polka dot pattern at 2 degrees. And again, the snapshots on 6 September show large error reduction with high resolution sampling and minimal error reduction with more coarse sampling. Yes?
So September 6th is a day, how many days after the estimation?
Okay, I think he asked how many days after, it started 1 May. So this is once at 4 months, a little over 4 months. So everything's well equilibrated. Other snapshots won't be identical, but they'll look very similar in terms of results. After a month, basically after a month, the model has equilibrated to the assimilation.
So you are simulating every day?
Every day, yes. And if you look over the 6-month analysis period, 1 June to 31 October, 5 months, I'm sorry. You see, this is a map of root mean square error calculated at each model grid point between the experiment and the nature run representing the truth. And for the this is for the 2-degree case. So what you see is how the errors are reduced on average over the entire analysis period. And basically you see, again, a sort of a dotted pattern. You see low or large error reduction in the vicinity of the observations, but in between observations, not so much. So again, the necessity to sample with high resolution to really correct mesoscale structure accurately is obvious in this case. Okay, now summarize part 1. Localization radius of 200 kilometers was determined to be a reasonable choice for our future work, so we're using that. Individual ocean profilers can only correct ocean structure in their immediate vicinity. And these results suggest it occurs primarily within 1 degree for large error reduction. One thing I have to point out is this result, it depends on the data assimilation system that we use. We're not using any of the more advanced techniques like 3D VAR, et cetera, to perform this work. So any DA system that more accurately estimates the background error covariance and the spreading may reduce the severity of the problem I've shown here. But I think this situation will affect all DA systems. Some may work obviously more accurately than ours since we're new to the game, but this is an issue that has to be considered when we're trying to initialize an ocean model for forecasting. And again, this demonstrates how validated OSSE systems can be used to really look at this in a rigorous quantitative fashion. The limited range of observation influence does have important consequences we have to consider. Profile surveys must cover the entire region over which accurate ocean forecasts are desired. And I can point out here that one thing I didn't point out is that you see the correction in the lower left, how it's really confined to the box of the sampling. You don't have to go far outside of that box to see that the mesoscale structure is no longer corrected. The system is so chaotic, the memory is so short in these systems that if you sample highly a certain region, outside of that region, the chaotic nature of the system, errors grow very rapidly, and your correction is confined to that region. Okay, profiles must be collected with sufficient horizontal resolution to accurately correct mesoscale structure. And I showed that with the spectral analysis, basically you're going to correct scales wavelengths larger than about twice your profiler separation distance. Don't expect that, in fact, you get errors tending to increase at smaller scales. So high resolution sampling is very important to correct the mesoscale. Okay, that ends part 1. Part 2, we're going to be using our system to initialize the coupled HICOM HWRF model. The errors I showed in correcting the ocean analyses used for initialization are significant. But what's that impact going to be on the intensity forecast? So to get an understanding beforehand, before we actually do the work, we need to understand the sensitivity of the atmospheric model to different ocean conditions and also to changing ocean conditions. And I worked with Gopal, Frank Marks, and Deborah Willey earlier on that paper that addressed these issues with an idealized HWRF study. I'll describe that in a moment. There are two factors that are important to understand how supplemental ocean profiler observations may affect predicted intensity. And one is the dependence of maximum predicted intensity on tropical cyclone heat potential. How much does this need to change to significantly change predicted intensity? If observations only make a small to modest change in heat potential, is that enough to change intensity significantly? We're looking at that in a quantitative sense, obviously. But we have some clues as to how that may work beforehand that I'll be showing. This all depends on storm size and translation speed, as I will show. The other issue in terms of model sensitivity is what is the rate of intensity change when a storm moves over a warmer or cooler ocean region? If the model responds slowly, obviously, or the storm is moving fast, it's only over a different heat potential region for a short period of time, you may not get a significant intensity impact. But what is the kind of the time scale of model response to these changes? Is it real short so that you can expect a rapid response, or does it take many hours for the model to really respond to a changing ocean? We looked at that issue quantitatively in this earlier study. Again, an important, it is storm translation speed is a major factor here. Now, the idealized study, I won't go into too much detail. I can provide a reference if anybody needs it, but it's a highly idealized study where we have an initially homogeneous atmosphere with an embedded initial vortex, an initial horizontally homogeneous ocean, no land, and we embedded a 1D ocean model in the HWRF model to do this study. The domain is shown on the left there with the initial vortex. To try to make this more realistic, we had to have the storm move relative to the ocean, but it turned out to be almost impossible to control storm motion through the atmospheric model. So in this case, I set up the model to actually bodily move the ocean model grid from west to east so that it mimics a westward propagating storm, with the ocean actually moving underneath the storm while the storm remained roughly stationary, wobbling a little bit. So we had to do some tricky things to make this work properly. There are three ocean model initializations shown on the right side. Initial temperature and salinity profiles. It's representative of typical Atlantic Ocean conditions for three different heat potential values, 150, 80, and 28 kilojoules per square centimeter. So we're going to look at the sensitivity of the model to these different ocean conditions. The initial temperature and humidity sounding for the atmosphere are also shown here. These were chosen so that the atmosphere is highly favorable for storm intensification. Two storm sizes are considered. There is a storm size dependence on how a storm will respond to the ocean. By initializing two initial vortices of two different radii, we were able to maintain through the forecast storms of two different sizes. I just call large and small. The large storm typically a 40 to 50 kilometer radius of maximum winds, small 15 to 20 kilometer. And the small storm is more like an Andrew type storm, where larger storm is probably more typical of many storms, especially the big ones we had last year. Okay, the first factor, the maximum intensity versus heat potential values. And just by keeping the ocean constant, even though the ocean's moving under the storm, the heat content has not changed on the storm at all. And we see sort of how the storm intensifies in the forecast here. And what we find is that for the three different heat potentials, you see the intensity reached by the storm is sensitive to the heat potential. But also, it's important to notice that even with the low heat potential of 28 kilojoules per centimeter squared, we still get a strong storm, 940 millibar central pressure. So this is significant because basically the sensitivities that I'll be describing here are between strong storms and very strong storms in changing the ocean conditions. The black line is an uncoupled run, as you can see, with the 150 kilojoule per square centimeter values. Basically, you don't change the intensity. It's only when you get under about 100, 110 that you begin to see the storm, the storm, final intensity of the storm gradually weaken. I ran a large number of experiments, and this intensity information can be plotted in a parameter space with the x-axis being storm translation speed, the y-axis being heat potential. The two panels on top show the minimum central pressure. Two on the bottom are for maximum wind speed. The left column is for a large storm. The right column is for small storm. And when you do this plot, what you see is that there are large regions, especially for small storms, where the ocean, this parameter space, where the ocean is not going to have a large influence on intensity. And for small storms, that extends down to heat potential of order 50 kilojoules per square centimeter. And for storms that are moving even quite a bit slower than average, you have to storm almost has to stall before you really see an ocean impact on the final intensity. For large storms, that's not as severe, but still there's a fairly large region of parameter space that where the ocean influence is going to be very weak. Now, in all these cases, you're looking at heat potential over 70 or 80 kilojoules per square centimeter. Those conditions are typical of the deep tropics. So it's been well known that storms in the deep tropics have shown relatively less impact of changes in ocean conditions compared to, say, storms in the Gulf of Mexico, where you encounter a larger ocean signal. But this gives you an idea of where in the parameter space you're likely to see a large ocean response versus very little ocean response. I'll come back to this later when I show an actual example of a forecast. The second factor that I mentioned is that the model intensity response time. How long does the model take to respond? And just going back to the lower left panel here, in this case, we initialize two different oceans. With one, warm ocean, one ocean might be warm and cold or vice versa. And then with the ocean grid moving to the east, this was set up so that about forecast hour 60, the transition region would pass underneath the eye of the storm. And then we can see how long it takes the storm to respond to this. And this is shown in some Hub-Modeler diagrams here, where the change in wind speed is shown in the four right panels. And the top row shows the case where storm moves over a warmer ocean, and the bottom case shows where a storm moves over a colder ocean. And what you see here is that, for the most part, within about the first 5 or 6 hours, the model really hasn't had a chance to respond that much. But generally between like a 6 to 18 hour period after the transition is when you see the change really kicking in. So there is a significant time lag in the storm responding. It takes at least 12 to 18 hours or longer to really totally adjust to the new ocean. So the impact, what that suggests is that if a storm moves over a very small ocean feature, unless it nearly stalls over it, if it's only over a feature with warmer or colder ocean conditions for, say, 3 or 4 hours, the model may not have a chance to respond. So we'll have to consider that when we're doing our real analysis work later this year with the HICOM HWRF model. Okay, to summarize implications on the impact of supplemental ocean observations. Ocean impact tends to be very weak for moderate to large values of heat potential, and storm translation speed close to or exceeding average values. Large majority of storms in the deep tropics will not respond significantly to the ocean without very large changes in heat potential beneath the storm. If the assimilation of supplemental ocean observations does not produce large changes in heat potential, most storms will not be significantly affected. So, let's see, changes in heat potential must affect the storm over a sufficiently long time, several hours or longer, for the intensity to be significantly affected. Again, I mentioned the small storm, but the storm has to spend significant time over a feature to really respond well. And one implication is because a single ocean profile only corrects the ocean within its immediate vicinity with great accuracy, for most storms, a single profiler may improve the ocean over a order 1 degree region, but that may not be enough to see a response from the hurricane model. See, multiple ocean profilers deployed over a large area and with sufficient horizontal resolution should be the best approach to make sure that the storm will feel the ocean changes resulting from sampling. And of course, the area size of the area depends on the storm translation speed. Now, I'm going to show an example where assimilation has significant impact. I think we've all seen this, Hurricane Gonzalo 2014, the work that Jilly Dong did, where we ran an Ocean OSSE, provided him with the two initial ocean fields, one from an unconstrained model, the second assimilating all ocean observations, including the PhD glider that was north of Puerto Rico at that time. And we ran twin forecast runs from these two experiments. And on the right, you see the intensity, pressure on top, wind speed on the bottom, and the black curve is best track, what was actually observed. Blue is from the unconstrained model, red is from the data assimilative model. And in both cases, more so for pressure than for wind, but you see a definite improvement in the forecast intensity. But I'd like to compare this to what we expect from that Idealized study results that I showed. One thing to realize about Gonzalo is there was about a 1.5 day period where it slowed to about 3 meters per second. That might put it in the region of parameter space where you might see more of an ocean impact. And the bottom panels, also the bottom panels show how much difference between these two forecast runs we had in the ocean heat potential. The lower left panel shows the observed heat potential from the AOML altimetry SST-derived product. The unconstrained run shows that the unconstrained run was too cold in terms of heat potential, whereas the data assimilative run was largely corrected in comparison to the observed values. And typically during this 2-day period, the unconstrained model encountered heat potentials between 40 and 70, whereas with the assimilation between 70 and 100. The difference average is about 40 kilojoules per square centimeter. So how does that fit into the thing? Okay, so Gonzalo was not a small storm, so I'm looking at the large storm parameter space analysis that I showed earlier. The red arrow shows the at the 3 meter per second translation speed, what we might expect in terms of intensity differences. And looking at difference in the pressure, central pressure between about 918 and 934, about 16 millibars, and wind speed of several meters per second. These values are actually fairly consistent with what was observed. Now the wind speeds here are in knots, but the actual differences that we would expect from this Idealized study were actually realized fairly well with this actual real forecast that we ran. So this shows that this type of idealized analysis can be used as a guide to what we might expect in terms of the storms we encounter in the future and evaluate. Some may not have very much ocean influence at all. Others may have a larger ocean influence depending on factors like size, speed, and this helps us understand that. Okay, implications for our planned OSE-OSSE work, including the hurricane intensity prediction, what we're going to be doing. Supplemental ocean observations must produce a significant change in heat potential over a sufficiently large area to produce a significant change in predicted intensity. It's a function of translation speed, storm size, et cetera. But for most storms, if TCHP is not corrected significantly and the area is too small, we may not see a ocean response signal in our work. A significant ocean impact on predicted intensity will be detectable if supplemental ocean profiler observations have several characteristics here. If they change the heat potential significantly over a sufficiently large area, so the storms remain over that area for at least several hours, then we should see a signal, translation speed being critically important. If the profiler observations are deployed with sufficient horizontal density, or ideally 1 degree or finer, to resolve mesoscale structure, we should see, we could very well see an ocean response signal. And getting mesoscale structure is important because the mesoscale structure influences the magnitude and pattern of SST cooling that occurs beneath storms. So getting that right is important. We're likely to see more of a signal for storms that are, for observations that are deployed away from the deep tropics where heat potential is smaller and large. Where away from the deep tropics where heat potential is smaller. You have larger OSSE signal when the heat potential is smaller. And also in regions where large heat potential changes are associated with mesoscale features. The Gulf of Mexico region being very obvious as you approach the Gulf Stream, where heat potential drops, but you have very large changes in cross regions. We're likely to see a much stronger signal there than we will in the deep tropics. Although in the right conditions, even in the deep tropics, slower moving storms, large storms, we can still detect in some storms, I'm sure, an ocean response signal. But this argues that when we do our OSSE and OSSE work, we need to work with a large number of storms. We're going to encounter storms which have almost no, the ocean has almost no impact on it in terms of changing intensity, but maybe a smaller percentage of storms where the ocean may have a large signal. And if we don't have a large sample of storms, we won't really be able to evaluate ocean impact on intensity for the panoply of storms that we're likely to encounter. The first two storms we look at might have little ocean signal. We can't get discouraged. We're going to encounter storms that have large ocean response signals. So that has to be kept in mind as we approach our work. So the storms we look at this year, especially the 2017 storms, will be an important factor, but we need 18, 19, 20 storms to really build up a good statistical understanding of how and under what conditions the ocean actually influences the forecast. And that's it. I'm tired, so I'll take questions.